Hello, everyone. Thanks a lot for this invitation to give this tutorial on score-based explanations in data management and machine learning. I'm going to cover several subjects. The first three are going to be on explanations in database, and the last three related to explanations in machine learning, in particular in classification. This is not expected to be an exhaustive and broad survey of the area. It is largely influenced by my own research in these topics. So let's concentrate first on databases. So in data management, we need to understand why certain results are obtained or not. We want to characterize and compute the reasons for those results. Those results could be query answers, some violations of semantic conditions like integrity constraints, and so on. And the database management system is expected to give explanations. And in our case, we are thinking about causality-based explanations. There are other related approaches like lineage, provenance, and actually we are going to see some connections with causality. In our research program, we have tried to understand causality in data management from different perspectives and trying to take advantage of the connections between those different perspectives or areas in which causality appears. So let me give you an example. We have a database here and then a conjunctive query, Boolean conjunctive query, taking value 0 or 1. In this case, this query has the join satisfied in the database. So the query is true, and we ask about the causes for this query to be true. And then we can see that actually, for example, removing this tuple SV from the database invalidates the query. That's exactly what the counterfactual cause is. So a tuple in the database is counterfactual cause for the query if the query is satisfied by the database, but when we remove the tuple, then the query is no longer true. So this SV is a counterfactual cause for the query. Yeah. But it might be the case that removing a single tuple is not enough to invalidate the query, so we might need to remove other tuples, and that is considered in the context of actual causality. By the way, before I continue, we should say that we are going to stick basically to these conjunctive queries, unions of conjunctive queries. So all the queries are going to be monotone in this presentation. That's why the relations matter here. So again, now if we take this other tuple, RAP, if we remove it from the database, it's not going to invalidate the query. We need the additional, removal of this other tuple here. So a tuple tau in the database is an actual cause for Q for the query if there is a contingency set, a set of tuples, such that tau, this one over here, for example, is a counterfactual cause for the query in the database from which we have removed this other tuple. Right? So that is why this is it's an actual cause for the query. This is also an actual cause for the query. The two of them need contingency tuples that accompany the tuple to invalidate the query. So how strong are the causes? For that we can use the notion of responsibility. The responsibility of an actual cause for the query, that is a tuple here, is 1 over the size of the smallest contingency set that is needed for tau to invalidate the query, plus 1. And if the tuple is not an actual cause, it doesn't have anything to do with the query. Basically, the responsibility is 0. So the responsibility of the tuple RAP is 1/2 because we needed an additional tuple in order to validate the query. That's why the size of this contingency set is 1. The same with RAB, RBB, and SA. They are also actual causes with responsibility 1/2. But the first tuple, the one that we consider here, SV, is a counterfactual cause, and the cause responsibility is 1, the maximum possible responsibility, because the contingency set will be empty in this case. So high responsibility tuples provide more interesting explanations. Actually, we can see responsibilities as scores assigned to tuples. And well, causality can be extended in different ways. I mean, for example, it can be extended to the attribute value level as opposed to the full tuple level. And also it is possible to define causality in the context of integrity constraints that have to be satisfied. But I'm not going to go into these two directions. It turns out that causality is connected to different areas. In particular, we have discovered some mutual reductions with repairs of databases with respect to integrity constraints. And the same applies with consistency-based diagnosis and abductive diagnosis. Yeah. These are two cases of what is called model-based diagnosis. So these connections have led to new complexity algorithmic results for causality and responsibility that are reported in this paper. Well, we can see causality as a way to provide diagnosis. That's in some sense similar to model-based diagnosis that I mentioned over here. But here in this case, what we have is actually, we are appealing to Judah Pearl's causality. The idea is to perform counterfactual interventions on a structural model that is of a logical nature or a probabilistic nature or the combination of both. So the idea is, here is we are asking what would happen if we change something in the model. And actually the idea is to identify causes through changes after the interventions on the model. And that is the underlying idea, the main idea behind this actual causality. So in the case of databases, you may ask, where is the model? Well, actually, it's very simple. The underlying logical model in this case is a query lineage. So we can see, I mean, counterfactual approaches, I mean, as something much newer, appearing in particular in explainable AI, newer in some sense than, say, model-based diagnosis. Counterfactual approaches are used to provide explanations, possibly in the absence of a model. That is also interesting, and we're going to see something about that. But the score can be derived from counterfactuals as well. Yeah? So we are going to see examples of this. In more general terms, explanation scores have become popular in machine learning. And they usually have a counterfactual component, explicit component, or a counterfactual flavor. I'm going to give example of both here. So responsibility can be seen as one of those explanation scores. Yeah? It is not the only one, and not even in the databases. So I'm going to mention a different one. This is the causal effect score. Let me give you an example to motivate why we thought about this alternative score. We have a Boolean data log query that becomes true on this database. That the data log query is basically it detects if there is a path from node A to node B. So this is the query. And actually this, the combination of this program with the extension of database E that captures this graph gives the answer yes to the query. There is a path. Actually, there are 3 different paths here. Yeah? So in this case, all the tuples are actual causes, because every tuple appears in a path from A to B. And what is interesting here is that all the tuples have exactly the same causal responsibility of 1/3, which may appear to be maybe a bit counterintuitive because T1 provides a direct path from A to B. So thinking of this example, and well, actually some other examples as well, we thought of at some point of considering an alternative notion or measure to that of responsibility. And that is the causal effect score. It was introduced a few years ago in a paper that at TAP 16. So again, the question is how the answer to Q changes if tau is deleted from a database. And what we want to do is produce an intervention on a structural causal model. Yeah? And in this case, as I mentioned before, the model is the lineage of the query. So in this example, it's not the same I had before. It's a simpler example. We have this database with this simple query, so conjunctive query, Boolean conjunctive query. It is true in this database. It is satisfied in the database. The query lineage instantiated on the database, this database, is given by a propositional formula, as found in propositional logic. So is this one. Basically, the query is true on this database if and only if this logical expression is true. When these propositional variables that stand for the presence or absence of tuples in the database, are true, and that happens when the tuple belongs to the database. So the variable is true when this tuple belongs to the database, and that is the only case where that happens. So in this case, this propositional formula takes a value 1 in the database. And we want to quantify the contribution of a tuple to the query answer. For example, this tuple over here is B, that is also represented by this variable over here as well. Yeah. So in order to do this, we're going to assign probabilities uniformly and independently to the tuples in the database. Okay. So we are transforming our original database into a probabilistic database where we have now columns here with probabilities. These tuples now may be in the database, may not be in the database, and there is this probability for being present in the database, 1/2. And they are independent tuples with independent probabilities. Yeah. So now each of the propositional variables that I had before standing for the tuples in the database, x taus, become independent, identically distributed random variables. And the query that depends on them becomes a random variable. Since it takes the value 1 or 0, it becomes a random variable with a Bernoulli distribution. So, and we can ask now, for example, what's the probability that Q, the query, takes the truth value 1 or 0 when an intervention is performed on the database, how the probability changes. So the interventions are going to be denoted in this way. That is the notation introduced by Yuga Pearl. This means makes variable x equal to x, where x is 0 or 1, I mean true or false, basically, in this case. Yeah. So if we change a value in the lineage of the query, well, we can start asking things. I mean, what is the probability that the Q takes the value y, that can be 0 or 1, when the variable x tau, standing for the presence of the tau in the database, is equal to x. Again, x equals 0 or 1. So basically, we have 4 cases here to consider. Yeah. So, for example, if we perform this intervention, that means we make x as be 0, or in other words, we delete from the database. The lineage that we have here becomes reduced to something simpler, where this is false, we're left basically with this part only. So this is the reduced or residual lineage of the query when we perform this intervention, yeah, making this equal to 0. Okay, so and we can play other games with these interventions, and the causal effect of the tuple we are dealing with is defined as the difference between two expectations, two expected values. The expected value of the query, that is a random variable, when we make tau equal to 1, that means it is definitely in the database, and the other expected value is the expected value of the query when we basically remove the tuple from the database. If that difference is positive, then we can say that tau is relevant for the query, and the difference gives us a score. Yeah. So just to continue with example very quickly, I mean, if we perform this intervention as we saw before, we have this residual lineage, and then we can ask what's the probability that Q takes the value 1 under this intervention, and then since these two variables are stochastically independent, we get 1/4. Yeah. The same when we do now SB equal to 1, I mean, it isn't definitely in the database, the lineage is reduced to this expression, yeah, and then we all we have to do is basically compute the probability of this expression, this probability, and actually I'm not going to perform the computation, but you get 13 over 16. And now we compute the expected values. And basically the expected value of Q when the XSB is 0 is reduces to the probability of Q equal 1 under this intervention, because the other value would be Q equals 0, and then if it multiplies the corresponding term, it disappears. Yeah, so we get 1/4. For the same reason, the expected value of Q under this intervention is going to be the probability we had computed before, for Q equal 1. Yeah, so we get this. So the causal effect of SB, this particular tuple, is going to be this difference that is 9 over 16, that is greater than 0. So this would be basically the degree of contribution of the tuple to the query result. Now, coming back to the original example for causal effect, the data log query can be expressed in this case very simple as a union of Boolean conjunctive query that has this lineage, yeah, basically the 3 different paths that we have instantiated on database. And then if we compute as before the causal effects for the tuples, we get this causal effect for this tuple, this causal effect for these 2 tuples, smaller than this one, and this causal effect for these 3 other tuples, much smaller than this and this. So in this case, the causal effects are different for different tuples or for different classes of tuples, and this gives us a much more intuitive result and responsibility. So this may look a bit ad hoc or arbitrary. Actually, we are going to see a different way of justifying this score that we have introduced here. And then the third approach that we're going to consider here is still in the context of databases, again, is based on results and techniques from coalition games. So again, the question is, what is the contribution of a database tuple to a query answer? And the idea here is that several tuples together are necessary to violate an integrity constraint or produce a query result. I mean, the outcome we are observing. So this is very much like players in a coalition game. Some may contribute more than others. We can use, in this context, then, notions from game theory. And the Shapley value is firmly established and widely used in game theory, coalition game theory. There are many applications. It is interesting to emphasize that the Shapley value that was introduced sometime in the 50s, 54, I think, is the only function that satisfies certain natural conditions. So it is a result of a set of properties of actions, right? So we can think of applying the Shapley value to query answering in databases. That is what we did in this recent paper at ICDT this year. So the Shapley value of a tuple will be a score for its contribution to the query result. So let me say a few words about the Shapley value. So we have a set of players D. In this case, it's going to be basically the set of tuples in the database. We have also a wealth distribution function or a gain function, in more simple terms, that assigns to sets of players, subsets of players, a real number. So this is the power set of D. So this is the wealth function. And then the Shapley value for the player P, a particular player in this set, is defined by this general expression. What is interesting to see here is here we have the gain function evaluated in the presence of P and here in the absence of P. Notice that here this S is a set of players that does not contain P. So here we are adding P to S to the set of players, and here we don't have the player in the set. So we are considering this difference in the wealth, basically capturing the contribution of P to the wealth function or the gain function. And then this is an average over all possible subsets of S, considering the order of appearance of the players in the game. So this number here is the number of permutations of players with all the players in the set S coming first, then followed by P, and then all the other remaining players. Yeah. So it's an average of contributions of P, considering all the possible different scenarios that may emerge, considering the other players. Again, it is expected contribution of player P and the all possible addition of P to a partial random sequence of players, yes, here, followed by a random sequence of the rest of the players. So here, for example, we have, we can start with this player over here. Its wealth alone is 2. Then we have a new player, the one over here, and then the common wealth is 7. So the contribution is 5, and so on. And if we are interested in this particular player, we see that in the end, this one is contributing with 4 to the wealth that we had before adding it to the set of players. So, and we consider all the possible situations for the other players and orders in which they participate in the game. Okay. Well, actually, there are results that show that Shapley is difficult to compute. It is provably sharply hard in general. And it also, we can notice that it has a counterfactual flavor in the sense that we are considering, I mean, what happens having P versus not having P as captured here in this expression. Yeah? So let's apply this Shapley value to our problem. So back to databases and query answering. We have all the tuples in the database as players. We have a Boolean query that becomes the gain function. So the gain function is very simple. So for a set of players, I mean, a set of tuples or a sub-instance of the initial instance, the gain function is 1 if the query is true in that sub-instance, or 0 if it is not true in that sub-instance of the database. So it's a very simple, but also natural gain function. We concentrate mostly in this paper at ICDT this year on Boolean conjunctive queries or a union of Boolean conjunctive queries and some aggregations on conjunctive queries, but I'm not going to say anything about aggregation. So if we instantiate the general formula for the Shapley value with this particular gain function, what we get is this expression, the Shapley value applied to this gain function. The difference here between having the tuple and not having the tuple. So this quantifies the contribution of tuple tau to the query result. So we obtain some results, an interesting result, like for example, if we have a query that is Boolean and conjunctive without self-joins, but self-joins, I mean, in conjunctive queries, I mean, are a source of complications and complexity that in this case, we are not considering as usually, I mean, especially when we have this kind of dichotomy theorem, we don't consider self-join. So if the query doesn't have self-joins, and if it is hierarchical, then the Shapley value for the tuple can be computed in polynomial time in the size of the database, this is data complexity. Otherwise, if it is not hierarchical, the problem is hard. Actually, it's complete for the class of functional or computational problems that can be solved in polynomial time with a call to an oracle in Sharp-P. And that is, let's say, sharp SAT. So that is an indication of the high complexity. So you could say, well, how difficult is it to check if the query is hierarchical? Actually, it's a very simple test. Hierarchical means that if you take any two variables in the query and you consider all the atoms that contain X and all the items that contain Y, well, one of these possibilities holds. One of the set of atoms contained in the other, or there are disjoint. So, for example, with this query, the set of atoms for X are these two atoms here. For Y, only this one. For Z, only this one. And we can see that this is containing here, this is containing here, and these two are disjoint. So this is a hierarchical query, and computing the Shapley value for this query for the tuple, I mean, would be doable in polynomial time in the size of the database. This other query, and H stands for non-hierarchical, and actually we can check that it is not. So the atoms that contain X are these two, the atoms that contain Y are these two, and this is not contained here, this is not contained here, and they are not disjoint. So it's not hierarchical, and actually it's a very interesting query, it's a very useful query that can be used to establish different, high complexity results in databases. So actually, these criteria that I have here are exactly the same criteria that we have for query answering over probabilistic databases. Yeah? The positive case for the normal time case, can be obtained by a dynamic programming approach. And the negative case, well, this requires a completely fresh approach. It's not something that we can get from the probabilistic database setting. This is, at least it's not obvious how to do that. So we can still use the same query though, but in this case, we have a reduction from counting independent sets in the bipartite graph. So, and what happens when we have hard cases? Well, actually, in the paper, we prove that we can approximate, in a reasonable manner, the result. So for every fixed query, there is a multiplicative, fully polynomial, randomized approximation scheme, which is considered to be something positive. Right? Okay. In the same paper, we also investigated a related score that is the Banzhaf power index. It is also widely used. Actually, in the spirit is similar to Shapley. The difference here is that the order is not considered. So here again, we have the differences in the query value between having the tuple and not having the tuple. But now we consider now the average over all the possible subsets. And this gives us the number of all possible subsets that do not contain the tuple tau. So, but again, this Banzhaf index is difficult to compute. It's actually probably sharply hard in general. But what is more interesting here for this presentation is actually the causal effect score that we introduced before coincides with the Banzhaf index. But at that point, when we introduced the causal effect, we had no idea about this possible connection with the Banzhaf index. So that is established in the paper as well. Okay, let's now move to the context of machine learning and classification, actually more specifically. So we have here a classifier. It could be a black box classification model, something that we don't have access to, to the internals, or something very difficult to analyze. Think of a very complicated neural network. And we have some entities that are going to be classified as 0 or 1. So L is labeled 0 or 1. These entities are represented as vectors of feature values. For example, could be an entity requesting a loan from a financial institution, and then we get the label 1, that in this case, for us, for the moment, is going to be the negative case, a rejection, no loan. So why? So that is the question that we want to answer. What is the explanation for this? Actually, the same kind of questions can be posed when we do have a model, access to the model, and we can easily understand it. For example, when they have a decision tree or a logistic regression model, the same questions apply. But having the model may have some interesting consequences in contraposition to the case where we don't have it. And all we have is basically an input-output relation associated to a black box. So again, in either case, the question is which feature values xi here contribute the most to the outcome, to the rejection in this case. So we want to assign numerical scores to feature values in the entity here. Yeah, trying to capture the relevance of the feature values for the outcome. In most of the cases, most of the scores that are used and the approaches that are used to explanations, there is always some sort of counterfactual intervention, either explicitly or implicit. But not always, but very common. So one of the popular scores is the Shapley score. Yeah, and actually this Shapley score comes from a particular application of the Shapley value, and it can be applied both with black box models and open models. Yeah. The journal version was just appeared this year. So what is the situation? Here we have now the features become the players in a game. Yeah? This set of features. The gain function, well, has to be determined by the entity that we are considering. We want to explain the result for this particular entity, right? So the gain function depends on E. So what do? We take an expectation of all the possible values for the label when the label is applied to different entities in our population, with the only restriction that when we have a set of feature S, the values for these entities coincide with the values for the entity at hand for the same set of features. So this is the projection of the entity, original entity, on this set of features. And then all these entities have to have the same values for this set of features, but the other values for the other features can vary within their domains. Yeah? So this is the way to basically to start trying to assess the feature values in the entity E. Yeah. So we can pick a particular feature now, and we compute the Shapley value for this particular feature. That is one of the players in the game for this gain function. So we, of course, this requires, I mean, some underlying probability distribution on the set of entities. The label becomes a random variable, a Bernoulli random variable, because it takes the value 1 or 0. So there is a probabilistic, I mean, setting it. So if we apply the Shapley value exactly as expressed at the beginning, I mean, with this particular gain function, we get exactly this expression. Now, check here. Basically, is going to be here the difference is between two expected values. One having the feature that we are trying to assess, the other term without that feature. Now we consider all the possible set of features that do not contain the one at hand. Yeah? So then this is a well-defined expression, assuming that we have, of course, the probability space underneath. And as I said before, I mean, we can apply SHAP, as you just saw. I mean, with black box or open explicit models, all we need is the input-output relationship. So if we have a black box models, if we want to compute this expectation, well, in principle, we can use the classifier many times, and with the entire space population and a given underlying distribution, but this is obviously not very appealing because we have possibly too many entities to try out. All the alternative would be to use a sample of the population, and we can compute weighted averages, which is much more natural and realistic in practice, and that is what people do when they don't have the model. When we do have the model, explicit model, let's say a decision tree, well, we still can play the game that we play here without considering the model, the internals of the model. Yeah? Or, well, now having the model, we can use the given classification model and compute the expectation. Yeah? Yeah. And it turns out that for some models and population distribution, SHAP computation can be done exactly and efficiently, polynomial time. So actually the original paper that introduced SHAP claims that it can be computed in polynomial time for decision trees, actually a bit more than that, random forests. And actually the whole SHAP measure, I mean, setting was introduced in the context of decision trees. The experiments are related to decision trees, and also the discussion relates to the decision trees. But of course, it could be applied to, well, not of course, but it could be applied to other settings. Actually, in a very recent paper, we proved that SHAP can be computed in polynomial time over a series of binary decision circuits used as classifiers. And in particular, this applies to decision trees. So it's a very precise proof of this polynomial time complexity for a series of nice classifiers. We consider in a different paper this year at SIGMOD, workshop at SIGMOD, another score, RESP, that is related to as you might guess, to responsibility and causality. So we have the same classification setting. We have a feature in the set of features. We have an entity. And now counter is a kind of a first step toward this score res. It's very simple, counter. What we do, we take the difference between the label for the original entity. Let's think of the one that was obtained by the person applying for a loan, minus the expected value of the labels, apply to all possible different entities in our population, under the condition that, well, the values for these entities are the same as the values for E for all the features other than the particular F. So basically, we are locally intervening the feature F, assigning possible different values and taking the expected value. The rest of the features keep the values as those as E. So this score can be applied to the same scenarios as the previous scores. It is easy to compute, as you can imagine here. And also it is very interesting that it gives reasonable results from the intuitive point of view. I mean, we perform experiments, and also in comparison to other scores. I mean, well, I may say more about this later on. So, but well, again, we have an expected value here, so that requires having an underlying probability space. There is no need to access the internal of the classification model. It can be applied with the black box model. That was the first idea. That's what we wanted to do. But there is a problem here. It might be the case that by changing values in one feature doesn't change the label. And when we have a change in the label is that when we start identify possible causes, right? So a problem is that changing one value may not switch the label. So no explanations are obtained. So what we can do is very natural, still in the spirit of actual causality, we can extend this score, bringing in the contingency sets for features that are other features that may have changes as well. And that is how the RESP score emerged from this basic one. And I'm going to give an example in a very simple situation where we have only binary features. I mean, the features take values 1 or 0 only. This can be extended later on, but just for the gist. Yeah, so here we have an entity that is being classified with this classification model. It gets the negative label 1. Then we say, well, let's change X into X prime, and possibly many X primes, and basically the label doesn't change. I mean, we have always get 1. So then we start playing with other values, let's say Z and Y, and we change them into Z prime and Y prime, still keeping the same value for X. And now we see, well, actually we still get the same value 1. But now suddenly, keeping these changes, we change X, this is the one we are focusing on, is changed into X prime, and now the label switches. So we can say in this case that X is an actual cause for the label 1, and these two values that were changed here become a contingency set for this value X over here. So very similar to the idea that we have under actual causality for database. Yeah. So when we only one change in the feature hand suffices to switch the label, well, in this case, we say that we have a counterfactual explanation. In more general terms, we're going to have something like this. We need other changes as well. So gamma stands, sorry, in this case, I'm denoting with Y, I mean the set of values that have to be changed together with the value X here. So basically, if I change the values in Y into Y prime, like here, I still have the same label, but if in addition I change X into X prime, I get the switch of the label value. So in that case, we say that X is an actual explanation, and this Y becomes a contingency set for this actual explanation. And now, what is the responsibility score? Basically 1 over 1 plus the cardinality of the smallest contingency set of features that had to be changed together with X. Yeah. So it is very natural. It's an extension of what we had before for databases. And now what happens when, well, let me give you a very quick an example here. I have this entity here. This entity gets the label 1. As you see here, if I change this 1 into 0 here, I get that this feature becomes a counterfactual explanation for the label 1. And now I can concentrate on this one here, and I see here this other entity that if I change 0 into 1 and 1 into 0, I need an additional change here. So this can be seen as an actual explanation, this 0, with a contingency set that is this one that also has to be changed. Right? So the responsibility for this feature here, for this entity, is going to be 1/2 because I need an extra change to switch the label. Yeah. So, well, this is very simple because these features are binary, but if we now have entities that may have other values other than 0 and 1, so then you have to basically consider all the possibilities, and that is how an expected value emerges. And I'm not going to enter into the details of the general RESP score. We're still, you will have the slide so you can check, what's going on here. I'm just going to give you the intuition. Here, again, we have an entity and the classification. We have label 1, and we have a very particular feature that we want to consider. Yeah. So basically, what you can see here, we have an expected value. This is very similar to the counter in the sense that we are basically allowing the values in F to be changed here, not the others. The only point that makes a difference with respect to the counter is that now we are considering for this F also a contingency set of features, and these W are the values that are taken by the new values that are taken by the features in the contingency set. So we get what I call the local responsibility score when we consider all these possible contingency set and possible assignments of values to the original values. So in the end, in order to get the responsibility score for the feature at hand for this entity, basically we take the maximum of these local responsibility scores under the condition that this gamma has to have a minimum size, that this is greater than 0, so there is a difference between the original label and the expected value, and the gamma and W, the values for the features in gamma, they have to satisfy the conditions that I skipped here, but they are all very natural. Basically, they were all illustrated in the previous example. So this is the RESP score. So we experimented with this RESP score. So actually, these are my final remarks. We compare all these different scores, counter, RESP, SHAP, and BANSAF. You can see the last paper I mentioned. We did this on top of Kaggle loan data, and we use XGBoost as a classification model that is opaque enough to make, for assuming it is a black box model. So, and actually very interesting results were obtained. As I said before, counter gives very interesting, simple, but very interesting and intuitive results. But of course, it has its limitations. And RESP extends this one, it's more subtle than counter. There is also another well-known score, is what we call Rudin's FICO score. It is an open model, and the score is model dependent. It depends on the actual components of the model. So actually, the score uses the internal outputs and coefficients of two nested logistic regression models. So that's why there are internal outputs and also there are coefficients. Well, all those things can be used, and you can define a score, yeah, for the different features in the game. Yeah. The model is designed for FICO data, so we use also the same FICO data, and we made experiments with that data, those data, And actually, it turns out that the counter and RESP give very similar results to the FICO score, but these are used as black box models, which is interesting. Well, the whole area is quite effervescent. Explainable AI. I mean, there is a lot of research, a lot of activity in this area now. The relevance can only grow. Actually, there are countries that already have legislation, others that are introducing legislation around explainability, transparency, and fairness of AI and machine learning systems. So this can only grow in terms of relevance. There are, of course, and I mentioned a few different approaches and methodologies, but it's very common to find causality and counterfactual and scores, I mean, as important players in this score definition game. So that is something that you can observe as a pattern. There is still, in my view, much research to do in the direction of using additional information, I mean, contextual, semantic, and domain knowledge. And some approaches may be more appropriate than others, and I propose a declarative approach in this paper that appeared this year. People have identified as a very crucial problem in this moment, I mean, to define, characterize what is a good explanation as needed for AI and machine learning, right? Not necessarily in general. And what should be the desired properties of an explanation score? These are important questions per se, but also if you consider what happened, for example, with Shapley. Shapley originally emerged from a list of desiderata properties that the score, the gain function was supposed to have, and then it emerged as the only function that satisfied those properties or had those properties. So the natural question is, could an explanation score emerge as the right one for certain explainability properties? That is a question that I think would be very interesting to answer and properly characterize and formalize. Well, this is the end of what I had to present. Thanks a lot for your attention and for the invitation again. Thanks a lot. Bye.